I hope you can hear me here. So this is not supposed to be a survey. This is not supposed to be a review of the recent result on the subject. Instead, I'm hoping to give you a slight taste of the subject, tell you a little bit about what it's about, and answer any of your nagging questions you might have about the subject. So as a result, I'm going to try to keep the references to a minimum, and in particular, I'm going to purge any references to myself, so you won't see my name anywhere on this slide. All right, so let's go. So the first question is, what is general about general relativity? And to answer that question, we have to start with the special relativity. So first, there was a special relativity, and in some sense, you can simply view this as a transition from the Galilei group of transformations, which are written up here. So this is from Galilei to Lorentz transformations. Now, if you look at the beginning, if you look at the early papers and books on the subject, in particular by Einstein himself, you won't see much of mathematics in there. Instead, it was all about clocks and trains and elevators. So just like in this picture, there's nothing else. And it's only a little bit later, mostly through the work of mathematicians, in particular Minkowski, where we understood that special relativity was about the geometry of Minkowski space. So what is Minkowski space? It's very simple. It's just a four-dimensional space-time, R3 plus 1, but endowed with a Lorentzian metric instead of a Riemannian metric. So that's the form of the metric. And what's interesting about this metric and this space-time is that it distinguishes different directions. So unlike Riemannian geometry, where all directions are born equal, here we have three distinct directions. One is the first one, the time-like direction, so which sit inside this light cone. We have the space-like directions, which are outside of the light cone, and we have very special directions, so-called null directions, which span the light cone both to the future and the past. And how do they define? They simply define as the vectors on which this metric vanishes. That's why they're called null. Okay, so that's the geometry of Minkowski spacetime. Now, null cones, we can picture them all we want. It's very nice, but how do we actually picture the whole Minkowski spacetime? In particular, so that I can fit it on this particular screen. So one such depiction can be obtained by compactifying Minkowski spacetime. And here is we're going to do this compactification in two stages. First, on the left, so we're going to bring the infinity to finite distance, and the fact that this is infinity reflected in the fact that these are dotted lines as opposed to solid lines. So I compactify to infinity, and then I want to point out several interesting features. So first of all, these dotted lines here, 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 and here. This is called null infinity, future null infinity and past null infinity. This is where light goes. If you have a source of light and you just follow it as it propagates, it eventually goes to null infinity. So if it goes to, the future, it's the future null infinity. If it goes to the past, it's past null infinity. Now, there are two of them here in this picture. Well, because I'm still not fully compactifying. I'm not suppressing the sphere direction, the action of the FSO3 on Minkowski space. So that's why you see two copies of them here. Now, the future time-like infinity, so that's where time-like observers go. It's been compactified and became a single point at infinity. So the future null infinity is blown up. The future time-like infinity is compactified to a point. And the same thing happens in the past. Now, the second stage of this compactification is that, well, there's no reason for us to look at the spheres. Why don't we just suppress them to points? And in that case, this picture becomes this picture, where the line gamma is nothing else but the center of symmetry. This is where R is equal to 0. And then we still have the future null infinity, the past null infinity. This is future time-like infinity, and this is space-like infinity, where again, which is compactified to a point. So the nice thing about this picture is that you can read off all the causal relations between observers, between different events from this diagram. Light propagates at 45 degrees, as time-like observers go basically at the lines up and down, not necessarily straight lines. Everything can be read off from here. Very good. So that was special relativity. Now, what about general relativity? Now the game changes. Instead of understanding properties of a fixed geometry, Lorentzian geometry, we now let geometry be unknown as well. And so what is the subject? What do we study here? We have space-time geometry, where we have gravitation and matter. The gravitation is encoded on the left-hand side of the Einstein equations, and it's represented by, so manifold, four-dimensional manifold M, as opposed to Minkowski. We have a metric G, which is now unknown instead of the Minkowski metric, and we have the external fields, which represent matter. Anything that has to do with geometry is on the left-hand side of the Einstein equations. G alpha beta is the gravitational tensor, which is nothing else but the Ricci curvature of the metric G minus a half metric G times the scalar curvature. And the right-hand side, well, you see the energy momentum tensor of matter, which is unspecified here. And you also see a cosmological constant, if you wish to include cosmological constant in your Einstein equations. So examples of matter. Well, the simplest one is when we simply take T equals 0. That's vacuum, no matter. We can include the simplest possible matter, which is we can couple Einstein equations to a scalar field. So this is just a single additional degree of freedom given by a function phi. This is an energy momentum tensor. And it turns out that because of the condition that the gravitational tensor is always divergence free, it forces an additional equation of motion on this additional degree of freedom, so that phi obeys a wave equation with respect to the unknown metric G, with the right-hand side being equal to 0. Very good. Now, one thing to notice is that it's very tempting to think that geometry is on the left, matter is on the right. But if you look at the form of this energy momentum tensor of matter, you see that the metric G appears in the expression for the energy momentum tensor. So the geometry is also on the right as well. So the right-hand side is not given to us. Everything is unknown here. Other examples, Maxwell field, perfect fluid. So I'm not going to go into detail about this, but for depending on your needs, you need to consider different sources of matter, and you need to solve coupled equations. Very good. So how do we view this? Well, special relativity is part of general relativity. So Minkowski spacetime is a solution of the Einstein vacuum equations. It's flat. It's not just Ricci flat. There is no matter. So it's a solution of the Einstein vacuum equations. So that's not a very interesting example. The first interesting example shows up here. And interestingly enough, it was actually written down more or less in this form, but not in this picture, in this pictorial form, only a couple of months after Einstein formulated theory of general relativity. So that's the Schwarzschild spacetime. And you see that so this picture of compactification of our spacetime is typically called Penrose diagram. So the Penrose diagram of Minkowski space is very, very different from the Penrose diagram of Schwarzschild spacetime. Now, like I said, this pictorial representation of Schwarzschild metric, or Schwarzschild spacetime rather, was actually not understood in 1915 or 1916 when Schwarzschild wrote down the expression for this metric. It was understood much later, about 40 years later. So it took a while before understanding that this is the correct picture of Schwarzschild spacetime. What is the problem? The problem is very simple. If you look at the expression for the metric, you see that when r is equal to 2m, the expression for the metric degenerates. So you might be tempted to say that this spacetime is singular, and the singularity happens when r is equal to 2m. However, and that's what took about 40 years, in reality a little less, but that's the fact r equals 2m is not a singularity of the metric. It's just a singularity of the coordinates that you use to describe this particular metric. Nothing singular happens at r equals 2m, but it does signify that something interesting happens at r equals 2m. So if you compare these two diagrams, this is there are common features. There is a future null infinity, exactly as in Minkowski spacetime. This is where all null geodesics go. There is a similar thing in the past. That's fine, but we're missing r equals 0. In this picture, we're missing the axis of symmetry. In this picture, r equals 0 is actually here. It's horizontal rather than vertical. And it's not a part of our spacetime because that's actually a singularity. Because if you look at this metric, there's another singularity that you see in this metric. It's r equals 0. And that is a known as singularity. That's the singularity of Schwarzschild. But it becomes space-like rather than time-like curve as in the Minkowski metric. Now, where is r equals to m? Well, that's r equals to m. These lines, diagonal lines, they're r equals to m. And that's called, there's no singularity. That's just this lines that separate the exterior region of Schwarzschild from the region of a black hole and the white hole in the past. So that's an example of a spacetime with a black hole. I'm going to come back to it. Now, the other difference with Minkowski spacetime, as you may notice, is that if you look at this particular curve that passes through the spacetime, so which gives you a space-like slice of the Schwarzschild spacetime, it actually has two asymptotically flat ends, as opposed to Minkowski spacetime, where there is just one. So there's one space-like infinity. Here, there are two of them. And this is one, and this is the second one. And this is done so that this spacetime would be complete. So that's done. You have to attach the second end for completeness. Very good. So that's the first highly non-trivial example, and we'll come back to it for various properties in a little bit. So what is mathematical general relativity? Well, it is a study of space of solutions of the Einstein equations and associated geometric phenomena. What it's not is that it's not a construction of explicit solutions, which is actually quite popular and useful, but that's not what mathematicians do. Well, we're not particularly good at constructing explicit solutions. We also not in the business of modeling approximate alternative or high order schemes or theories. So again, this is something very popular in the physics community because it reflects their needs, but this is not what mathematicians do. We try to solve existing theories rather than formulating new speculative theories. Okay, so how do we study space of solutions of the Einstein equations? And what is the space of solutions? So we have the Einstein vacuum equations, which tell us something about Ricci curvature of a Lorentzian metric. How does one solve it? Well, the first observation is that we can actually parameterize the space of solutions by initial data. And that is a highly non-trivial statement, which again is going to show up later. But what is initial data? Well, initial data is a particular snapshot of our spacetime. So we take a picture, and then we want to use this picture at a given moment as our initial data from which we want to construct the spacetime manifold. So it consists of a Riemannian manifold, which is three-dimensional, a Riemannian metric on a G naught, the second fundamental form K naught, and a collection of initial values of external fields. What is the second fundamental form for? The second fundamental form serves the way to describe how this Riemannian manifold is going to embed into our higher dimensional space-time manifold. Okay? So here's a picture, and I'm going to illustrate of what is the initial data in this picture. So this is our spacetime. The initial data is right here. This is vaguely this yellow curve that passes here. So this is a snapshot of our manifold. This is one dimension lower than the spacetime manifold. This is where we prescribe our initial data, and then we just we paint it up. So we evolve our spacetime from this initial data. Very good. So how do we talk about mathematical general relativity? What language, what perspectives do we have? So the first perspective is a PDE perspective, because at the end of the day, Einstein vacuum equations, there's a word equations there. So there's something about they're not ordinary differential equations, they're partial differential equations. So we have a PDE perspective on it. So they're evolutionary PDEs, and I'm going to show you a little computation which actually goes back to Einstein himself. So suppose that you want to solve the equation Einstein vacuum equations, or Einstein equations coupled to a matter field, which is not specified here. So I want to understand the expression for the gravitational tensor in terms of the Lorentzian metric. And what we're going to do is that we're going to assume that the metric G is represented by Minkowski metric plus something very small. And I'm going to expand this in terms of that smallness. Now, it turns out that it's convenient to form a slightly different quantity out of this small perturbation h, which is take h and subtract a multiple of its trace. That's just for convenience. So when you expand the gravitational tensor, you discover that the left-hand side of the Einstein equations has the following form, where each term on the left-hand side involves two partial derivatives of this tensor gamma that you see. Now, the first one is significant because the first one is nothing else but a particular combination of second derivatives, which is the box, or the representing the wave equation on Minkowski space itself, because we're expanding around Minkowski space. So it's not surprising that you have something related to Minkowski space showing up here. Now the question is, what do you do about the rest? What you do about the rest is that you notice the following, that the general relativity by design is a covariant theory. So it looks exactly the same in any chosen system of coordinates. So it's up to us to choose a particular system of coordinates in which to write down the equations. Another way of saying is that we can choose a gauge. And one of the simplest gauges, at least at the linearized level that I'm showing you here, is the so-called Hilbert gauge. Though Hilbert didn't really have much to do with this. This is, again, a gauge used by Einstein. And the gauge simply tells you that you can choose this tensor gamma to be divergence-free. I'm using the silent summation over repeated indices as it's typically done. Okay, so if you do that, if you choose this gauge, then you see something interesting. You see that all these extra terms disappear, and you end up with the wave equation with the right-hand side given by matter for the tensor gamma. So that is the first evidence of the Einstein equations being hyperbolic. That also shows you the first evidence that gravitational waves do exist, because it is, after all, described by the wave equation given by the matter appearing on the right-hand side. So if the upshot of this is that if you give space-time a little bump, then this bump will propagate out exactly like waves, any waves propagate. So that's a PDE perspective. Now, there is a geometric perspective, because, of course, we are talking about a manifold with the Lorentzian metric on it. So we can use geometric language. We can also try to understand and study geometric properties of this manifold. So we talk about time-like, space-like null geodesics. We talk about null hypersurfaces. We already talked about Penrose diagrams. We already mentioned curvature. So this is all geometric language. We can forget about PDEs. We can try to understand geometry of the corresponding manifold. So again, let me give you one example. So one particular aspect of geometry that shows up here is the geometry of initial data that you need to prescribe for the Einstein equation. It turns out that the initial data is constrained. You cannot prescribe Riemannian metric and the second fundamental form arbitrarily. They have to satisfy a certain compatibility relation, which goes by the name of constraint equations, which are written here. So this is the system of constraint equations, which tie the scalar curvature of the metric G0, the second fundamental form K0, the trace of it, and also tells you that the second fundamental form has to be in some sense divergence-free with respect to the metric G0 again. So, well, examples. Well, we can take Euclidean space with a standard Euclidean metric on it. That's going to solve these equations because everything is going to be equal to 0 in this expression. Okay, do we have more interesting examples? Yes, we can study so-called asymptotically flat initial data. What does it mean? It means that as our initial manifold, we're going to take something which looks like Euclidean R3, at least at infinity. So if you remove compact set, we want to say that it should be diffeomorphic to R3 minus a ball. And then what should our metric look like at infinity? Well, we're going to expand it in the inverse powers of R. The first term should be purely Euclidean. The next term should be m over R, where m is a constant. And there are higher order terms which decay faster in R. And we're going to make the same assumptions on the second fundamental form K0. So in this case, because of the constraint equations, it turns out that this constant m that appears in the expansion has to satisfy the condition that m is greater than or equal to 0. This is known as the positive mass theorem due to Shane and Yao and Whitney. So that's an example of how geometry shows up here. In particular, if you study, let's say, initial data geometry, then manifolds of positive scalar curvature will be particularly important here. And then finally, we have the physics language. And again, we mentioned some of them. We talked about observers, which are causal geodesics. We didn't talk about determinism yet. Hopefully we might. So it's the fact that the manifold should be uniquely determined by its initial data. We can talk about redshift. We can talk about surface gravity. All of these are physics concepts that appear in general relativity because it is a theory that comes out of physics. Very good. So then, how do we talk about this? Okay, we know the languages, then we have to talk about methodology. And I want to bring your attention to basically two different methodologies that historically existed in the subject. One I call teleological, and the second one I called evolutionary. So what is a teleological approach to the Einstein equations, to general relativity? Teleological approach is you assume that the manifold already exists. You give it some properties that you think are reasonable or physical, and then you study its properties. So then evolutionary approach, by contrast, does not assume that you have a manifold. It starts with initial data, and then it constructs the manifold and looks at what you get. Okay. So again, I want to illustrate two approaches. So what is a perfect example of a teleological approach is a very famous result, which is incompleteness theorem by Penrose from 1965. Now also known in the literature often as a singularity theorem, although there are no singularities in his theorem, so it's a misnomer. The correct statement is that it's an incompleteness theorem. On the left, you have the assumptions. You assume that you have a null energy condition. You don't have to bother with this. I think Robert will talk about what null energy condition is, but you can assume that this is a theorem about vacuum, or at least for matter which satisfies reasonable assumptions. You have to assume that the spacetime possesses a non-compact Cauchy hypersurface. Let's say we have an example of asymptotically flat initial data. R3 is perfect. And then finally, and that's the most important assumption, you have to assume that somewhere in your spacetime, there is something that's called a trapped surface. I'm going to show you a picture of what a trapped surface looks like. But basically, you should think about it like this, that if you think in Minkowski spacetime and you take a sphere and you try to think of the sphere as a source of light, there are two ways that light can propagate from the sphere. One is out, and the other one is in. And when it propagates out, the corresponding spheres that are developed from the original sphere increase in its area, and the ones that go in, they decrease in area. A trapped sphere has a property that in both directions, the area decreases. So that's something that does not exist in Minkowski space. That something happens under the influence of gravity. The gravity pulls everything in, and so things start to collapse inside. So you have to assume that such a thing exists in your spacetime. What's the conclusion? Your spacetime is geodesically incomplete. So this is an interesting statement, and of course you have to understand what geodesic incompleteness means, but it tells you something. You assume something about your manifold, you hope that it's reasonable, and then you drew a conclusion. And this is a beautiful result, which is based on basic monotonicity that you see in the Einstein equations. And I just wrote it down. It's known by the name of Brachet-Doré equation, and it tracks the evolution of the congruence of null geodesics. And this should be a familiar equation to many because this is nothing else but a Riccati equation, which has a property that for some initial data, it blows up in finite time. And that blow up is responsible for geodesic incompleteness. There's no singularity because of that blow up. It's just geodesic incompleteness. So you should compare it with a classical Bonnet-Myers theorem in Riemannian geometry. Now, here's a picture of a trapped surface, which is not much of a picture. This is just an artistic interpretation of this. Okay, now, if you go back to this, well, let me just go to this picture. So this is another representation of how a trapped surface may actually form in your spacetime. So you see that if you look at your surfaces here, the light flows out, and here it increases the area. As you go in, it increases less, and less, and then finally you have a surface here. You start, and eventually it gets pulled in and gets trapped. So that's how it can develop. Now, if you look at this result, then there are two questions that remain unanswered. They always are in the teleological approach. How do you find a spacetime which possesses all the properties that you assumed? Well, in this case, this was a beautiful result because we could actually find plenty of such spacetimes. For instance, Schwarzschild is a spacetime which satisfies all these properties. In particular, it has plenty of trapped surfaces in it. But the big question is that, okay, Schwarzschild is a nice example. This shows that this is something open. This is a stable condition. But can we find a spacetime where initially you have no trapped surfaces and then trapped surfaces develop in evolution? And then the second question that remains unanswered is that, okay, M is geodesically incomplete, but what happens with those incomplete geodesics? The second one, the latter question, is very difficult. The former question is extremely difficult as well, and it took about 40 years to answer. And it was answered in the work of Christodoulou, which I want to highlight as an example of an evolutionary approach to general relativity. So you assume none of the properties, you start with initial data, and you ask the question, can a trapped surface form in evolution? In particular, when you have no matter, which can actually drive formation of trapped surface. And the answer is yes. So Christodoulou in 2008 gave sufficient condition for evolutionary formation of Trapp surfaces. Okay. So again, back to this picture, this is what happens. Somehow your space-time is such, it has so much curvature in it that it distorts the geometry and makes absolutely normal surfaces eventually collapse and become trapped. And then Penrose's theorem kicks in and tells you that such space-time will be incomplete. All right, so now with teleological arguments, certain care should be required, in particular because in some cases, the assumptions that you made on your spacetime may turn out to be unreasonable. And here I want to highlight another, it's not a theorem, it's a proposal by Penrose, who assumed that it would be extremely important to study a so-called asymptotically simple spacetimes. In other words, you want to focus your attention on spacetimes which allow for smooth compactification. Minkowski spacetime allows for smooth compactification. So let's just look at the class of spacetimes, whether they exist or not beyond Minkowski spacetime, with the property that when you compactify them, you end up with a smooth spacetime. If you do that, you can actually draw pretty striking conclusions. In particular, you can immediately understand asymptotic behavior of all fields of null infinity, which goes by the name of peeling in the physics literature. However, as it turned out, assumption of asymptotic simplicity, assumption that the conformal compactification is smooth, is not particularly physical because it turns out to be non-generic in evolution. If you start with generic initial data, the resulting spacetime cannot be conformally compactified in a smooth fashion. So that is out. Okay? It's very good, but not particularly useful at this point. All right, so what do we study? Well, from the point of view of Riemannian and Lorentzian geometry, we can study positive mass theorem, which I already referred to. We can talk about initial data engineering, Penrose inequalities, splitting theorems, horizons. From the point of view of evolution problem, we can study geometry and hyperbolic equations, existence, formation of singularities, stability, and rigidity. Now, the evolutionary perspective is much closer to my sensibilities. So if you look at the point of the evolution problem, at the end of the day, it turns out to be all about properties of the what's called maximal Cauchy development. So I need to tell you a little bit about what maximal Cauchy development is. And I need to come back to this picture again. So we start with our initial data and we start solving for our spacetime. And we can solve in different regions at different speeds, so to speak. And eventually we come to a red region and we cannot go past the red region for one reason or another. Our geodesics become incomplete. So they become incomplete here, they become incomplete here, they become incomplete here, and here it's all yellow. We can continue as far as we want. So maximal Cauchy development is the maximal picture that you can paint here until you run into red. And red represents the boundary of our maximal Cauchy development. And what we want to understand is, why did we get the boundary? What happens at the boundary? Why does the evolution stop? All right. So let's try to formalize this. So we give our initial data. This is here. Everything is described. We have a couple of theorems here. So there's a theorem due to Choquet-Brouillard from 1952, and an extra theorem which then completed the picture of Choquet-Brouillard and Gerrish from 1969. And it basically tells you that you can, given reasonable initial data, you can always solve for a bit. And then in 1969, you can then show that you can always solve up to the maximum. You don't know what the maximum is, but it just tells you that it exists. Okay? What is it based on? The proof of this result is basically based on the calculation that I showed you at the linearized level. You exploit covariance, you impose what's called the harmonic gauge, which is the nonlinear analog of the Hilbert gauge that I showed you, goes by the name of harmonic gauge or harmonic coordinates. So these are coordinates like this. And you observe that in this case, the Einstein equations, let's say without matter, reduce to a system of quasi-linear wave equations. And then you show that you can solve this system, at least locally in time, and then you start maximizing that time. And that's how you end up with a maximal Cauchy development. So global structure of the Cauchy development, of maximal Cauchy development. Remember, we solved it up to the red, we now have a boundary, and we want to understand what happens at the boundary. And the picture at the boundary can be quite complicated. So there is one version which is the picture on the left, where we have the null infinity. There was forget about the surface of the star. We had our initial data. We solved. We obtained the future null infinity. We obtained there's a black hole region here, and inside the black hole, like in Schwarzschild, we have a singularity. That's the boundary. We reach this boundary in finite time, and we cannot paint past this boundary because there is actual singularity, so we cannot extend. So that turns out to be both happen and also desirable from a physics point of view, because, and I'll explain this later, the singularity here sits inside the black hole, and that's where we want it. Now, there's another picture that could happen, which is where we have our future null infinity going up to here, but we have a black hole, but instead of the inside the black hole, instead of having this nice horizontal picture with the singularity, we have something which is called the Cauchy horizon, which extends from here to here, right here. And it's at 45 degrees. There is no singularity. And it turns out that what happens is that you can actually extend your space-time in a non-unique fashion past that Cauchy horizon. Now, that's not part of the maximal extension that I was telling you about, because once you go to the other side of this line, you have null geodesics which do not go back to your initial data. So in other words, the solution here is no longer predicted by what happens at initial data. That's not part of the maximal Cauchy development. The emphasis here is on Cauchy. So that picture is extremely undesirable because it signifies end of determinism. We can have a solution which is not uniquely predicted by initial data. So I mentioned determinism before. All right. So now we have, relative to both of these pictures, we have several conjectures in the subject. The first conjecture goes by the name of weak cosmic censorship. And it says that for generic data, singularities should be hidden inside black holes. So in other words, for generic initial data, not what I intended, our picture should look like this. We have a singularity, we have a boundary of Cauchy development, but it's hidden inside the black hole. I'll tell you a little bit about the alternative. The second conjecture goes by the name of strong cosmic censorship. So, but it's not stronger than the weak cosmic censorship. It's just about something else. And it tells you that for generic initial data, black holes should terminate in singularities. In other words, no Cauchy horizons. So it means that for generic initial data, we do not expect to see this picture and the end of determinism. We don't want to see Cauchy horizon. We don't want to be able to extend our spacetime in a non-unique fashion. Now, these conjectures are very hard. And the reason why they're hard are multiple. One is that the word generic. In order to understand that something happens generically, you have to then be able to solve evolution problem with generic initial data. Generally speaking, Einstein equations not, that is very poorly understood in evolutionary PDEs. Sometimes, and we have partial answers, but not full answers. Instead, we much better, when we deal with evolution problem for nearly specific initial data, stability problems, near Minkowski, Kerr, two-body problems, singularity creation, we're much better at that. And of course, they all have to be they have to become a part of the solution to these conjectures. All right, so let me unpack some of the things that came up here. So first of all, what is a black hole? Well, here's a picture of a black hole. It doesn't tell you much. So now maybe a little better picture from a point of view of Penrose diagram. A black hole is something very simple. It's something which is complementary to future null infinity. You see, we look at the region where all null geodesics go. Null geodesic of infinite extent. That's future null infinity. When we look at the past of future null infinity, and we'll see that there is a region here which is not included in the past of future null infinity. That is the black hole region. This is the region from which light cannot escape. How the black hole ends, that's a separate problem. Whether there is a singularity or something else, again, that's not a part of this picture. This is just explaining to you what a black hole is. Black hole is a global notion. All right, do we have examples of black hole solutions or solutions which contain black holes? Of course, we already showed you Schwarzschild. There's another example here. We have plenty of examples of the spacetimes with black holes. What about singularity? So I want to go back for a second to the weak cosmic censorship conjecture. It says that for generic data, singularities are hidden inside black holes. So the key here is that you allow singularities but you say that generically they should always live inside the black hole. So in principle, it allows for the possibility that the singularity is outside the black hole, which is very undesirable from a physics point of view, because then our observers that do not fall inside the black hole can see such a singularity and get terminated in finite time. So what is a singularity then? Well, it's complicated because the general notion is rather subtle. It may depend on how you define what's singular and what's not. But vaguely, you should think that it's something where curvature blows up. And again, even in that case, care has to be taken because the notion of curvature, we don't have a notion of non-degenerate length. So we don't know really how to measure strength of curvature, except we can do it through curvature invariance. That's maybe the surest way to measure. Can singularities form? Well, yes, for instance, in Schwarzschild black hole terminates in the singularity. Some other black holes can terminate in the singularity. And then, can the singularities live outside the black holes? That's something that would violate the weak cosmic censorship. And the answer is amazingly yes. And that's why the word generic is necessary in the weak cosmic censorship conjecture. We have to exclude non-generic examples. The examples are few in between, and there are constructions when the matter is present. So if you remember the Einstein scalar field model that I showed you, Christodoulou in early 90s constructed naked singularities for that particular model. And then it spurred the whole direction in numerical and physics literature called critical collapse, which I'm not going to go to. And when there is no matter, then the result is very, very recent, and it shows existence of naked singularities and is due to Schlappentoch-Rothman. Okay, so what is a naked singularity? So this is a singularity hidden inside the black hole. This is a singularity that's naked. So there is no black hole here. The null infinity, it's incomplete. It has finite length because this singularity influences and terminates the singularity and terminates the null infinity. So the observers that travel here, they will see information propagating from this singular point to them in finite time. All right, I should finish up. Right. So here is a picture of naked singularity for you. So finally, let me just end this at the Cauchy horizon. So remember, this relates to the strong cosmic censorship conjecture. We want our black holes end at the singularity. We don't want them to end with Cauchy horizons across which one may be able to extend the space-time non-uniquely. And it turns out that in some sense, strong cosmic censorship conjecture is already wrong. And that's the work of Defermos and Luck from 2017. They showed that it's possible to show that strong cosmic censorship is actually fails in the C0 category, not just non-generically, but in fact for an open set of initial data. So the word generic may not be sufficient for strong cosmic censorship conjecture, or at least one should acknowledge the word of topology in which one understands the strong cosmic censorship in that case. All right, let me stop here.